Thank you very much. So, hello everybody. My name is Nidal Benaloui. I think it's very difficult to talk after Philippe because her presentation is very, very good quality. And first of all, I want to say sorry for my poor language, English. I think there is some problem with the camera. And my presentation will talk about PLC, Programmable Logical Controller, commonly known as SCADA, Supervisory Control and Data Acquisition. You have all detail on this paper, but I'm here to talk about my paper and to present some demonstration if it works, I hope. So the agenda, first of all, I will introduce the ICS, Industrial Control System. Then I will try to explain in a simple word how it works inside. After, I will show you a simple code in C language talking about funny dynamically code injection. And normally, at the fourth part, I have a demonstration. I will talk about the equipment during the traveling plane with the protection measure after the incident. So I will show you a video of attack and the code which used to make this attack with some defense and countermeasure. And finally, I will conclude. And at the last, you can ask me a question. I will to say if the question is so difficult, I will answer it's confidential information. No, it's I will try to answer the question. So introduction. The aim of this paper is it easy to execute arbitrary code on a PLC without dynamic injection? This is a question. You have the answer. Yes, it's very, very easy to do it. How? By listening my presentation until the end. Huh? So, it's so. Where we find the ICS and what's the industrial control system? So the industrial control system, or SCADA, it's a system which provide and give the possibility to communicate with some equipment by remote action using a distant channel and a specific protocol. So we use the ICS, or we can find them in more industry. I put here some pictures. Food manufacturer plants, power plants, building automation system, nuclear plants. So we can find this equipment. And they work from since 20 or 30 years old. So be careful, you have also ICS or PLC in a fun fair, swimming pool. So dynamic injection can also cause damage if you don't be careful to this problem. A general picture of ICS. So, commonly we have 4 levels. The first level is composed by electrical engine, van, some sensor, actuator. So this basically are no intelligent equipment. Then you have the level 1 is the level of command and control, where we find the equipment that we're interesting in our presentation and in this paper. So PLC here. Here we have some PLC, maintenance laptop, our development like this. So I will show you, this is a station and a real station from Siemens to develop some code on this PLC. You have sometimes a distant equipment or a hotspot Wi-Fi, digital input, output, wireless, speed variator, something like that. So you use a bus here with a specific protocol like Profinet, Modbus, or Profibus. Donc specific protocol sometimes, and sometimes is a normalized protocol to communicate with between the PLC and the actuator or the sensor. Then we have the level 2, is the control and supervision. So sometimes when we talk about SCADA, so we talk about the control room here. Sorry. Sometimes when we go to see how what's SCADA control, so we go to this kind of room, but we should, the SCADA is all this part. All this part is the SCADA. And we have the third level, so we call it about operating management. In general, it's a level at like one factory, for example, or one ship, in which we have some servers, some IT computer to control and to manage all this infrastructure. And the next level, the level corporate or network, so we can talk about IT, but we have more and more some CAO which want to have the information of the engine, the quantity of the fuel on the ship, and more information collecting from all the factory at real time. So that's why we have a connection in general between the SCADA and the corporate information IT. So we can talk about this connection, but this is not the aim of this presentation. So I think that is clear. And the target of this presentation of the dynamic injection code is the PLC here. So I put two examples of PLC. This one, this target is the Siemens PLC, donc S7-300. There is a lot of kind of PLC Siemens, S7-100 and 100, 400 also. I put here another PLC for manufacturer Phoenix. There is also Rockwell, Schneider. So the objective of this presentation is not to show that the PLC of Siemens is vulnerable, but the same thing. Actually, we make we testing the same injection code on the other manufacturer, and I can say that it works on the other also. So what is a programmable logical controller? So I came here with an example of equipment in order to have an idea of the block of the equipment. So you can show here the red light, because during the travel they don't care with the equipment, so the interface internet communication doesn't work really. So we have here a power module, then the CPU, in which we can put the SD card here. This is proposed by the manufacturer, in which we have the code. So we inject the code in this CPU, in the SD card. We have then digital input and digital output. Also, we have some analogic input and analogic input, and we make a cable here, enter to the engine or to the actuator, and we can command it by the signal after programming. And at the last here, we have the interface internet communication module. So we have just to put the cable here, and you can communicate. So this is the major presentation. So in general, we use a Profinet cable like this. So this cable is given by Siemens, not specific cable, just to have a color information to connect the PLC with the laptop development. And so just we connect it to the dev station. The CPU of the presentation that we used here in my demonstration is a S7-300. Up to 32 memory internal, the SD card, simply SD card, and the program running on the CPU, the interface data with physical world as shown here. More simple, not to need to have a good comprehension of the equipment. You can also use a serial bus to communicate with the CPU here. We have two kind of protocol communication. MPI, this is a specific protocol communication with a specific serial cable of Siemens, and can also use the Modbus protocol. It's a serial channel communication also that we use specific parameters of Siemens to communicate between the laptop and the CPU. So we can say easily that this CPU is a small computer, like a Arduino, in which we inject the program and we communicate with the actuator. So let's talk about software configuration. What we have inside the PLC. So the PLC real-time digital computer used for automation. I don't need to repeat the definition of the equipment. Here we have an example of another model of SZ 400. So we have the power, the Poffiness connectivity, output, input. So we can use without connecting it. So we can write or source a program in SZ protocol and inject it through the PLC without need to connect it really to the engine or to the actuator. So inside the PLC, after the hardware, we have the firmware with the operating system. In general, it's a Linux embedded, modified by Siemens or by the other. Sometimes they have also the VxWorks operating system. We have also a middleware interface between the programmable logic, so between the MC set code coded by the developer, and finally we have the application. I put here some general application like a web server needed to control and to modify the configuration of PLC by the developer by using internet communication. So, PLC operating principle. So, this is a picture to which we understand. So, on this picture, we have the composition of the program through the PLC. So, the first file, code source file that we have, it's the OB1. So, OB1 is the same thing like the main file in the language, C language. Then we have some other block, FB, FC, functional block, functional system also. So all this block is put and compiled on the laptop station and put it throughout the PLC. And at each cycle, the PLC at the first step initiate the program counter. So put, for example, 0 in the flag on the CPU. Then it read all the input memory from the input digital or analogic input. They read this information. They store them on the internal memory. Then he executes the program which coded by the developer. At the end of the program, the result of the execution program give the output and put this output on the output analogic or digital analogic. They affect them. At the end of the cycle, the program or the CPU come back at the first state and do it again. So this is for the principle of the execution, main principle of execution of the PLC. We have also some memento. So memento is like some variable used in memory. We have a specific number of memento which can use it to put it information in order to make communication between some organization block or functional block. So we will see that For example, if you want to say that the engine is stop, so you declare one memento and you say, for example, if the byte of the memento is put to 1, the engine is start, and if the value is 0 or false because it's analogic or Boolean interpretation variable, so the engine is start. So by this kind of development, our sourcing code, we will understand that is very easy for someone who want to talk with the engine to put the flag by remote action or by injecting a dynamic code throughout the PLC. Of course, you should first of all to understand what's the memento used to control which equipment, which remote equipment. So here we have some example of code that we can use to develop into the PLC. So we have a logical development. So sample kind of development. We have the contact development like electrical development, and the list like assembly here. So more sample. And here we propose the algorithm in which we use to inject the dynamic code through the PLC. So first of all, we have developed a code by using Snapset library. So we can download the Snapset library on this web line. On this library, so we can call the function to connect to the PLC. So it's implement 300 SSET 300 PLC and other model. Then you download the original OB from the SSET PLC. So here I have the demonstration video that make this. Why we download it? Because first, before to modify the payload, we need to understand the code source, original code source, and the code source isn't clear. So it's not difficult to download it with this library. We open this OB1 file on the legitimate dev station. We modify the payload. For example, we change the sense of value, or we add a network in the code source to indicate a false information on the HMI supervision, like is done in Stuxnet. Then, when we want to upload the new corrupted OB1, we have first a condition. If the CPU memory is protected by a password, we should first bypass the password, because when we upload OB1 code throughout the PLC, first of all, the CPU check the time, the date of the packet. Then they check the CRC code, so the checksum. If they're correct, they verify if, or they check if there are remote passwords, throughout the PLC. If there is no password, so they replace and they erase the original OB1 by the new or the corrupted block injected. But if there are password, we should first of all put the password. So we have found on the internet some Python file or script that we can bypass the password by brute forcing the password, because you can make some attention to put the password, and there is no limitation. The number of limitation to try some password is not limited on the PLC. Or you can also read the specific area when the cipher password is put, then you brute force this on your PLC. So we have done this test in laboratory. And after this action, we upload the new OB into the SSET PLC. So we don't have no problem, because we have generated the corrupted OB1 on the laptop. So, and the SSET or TEIA portal of Siemens compute the new CRC and put it on the packet, so we don't have the problem to inject it. And at the last of action, we disconnect from the SZ PLC. So you should understand that the PLC don't need to reboot or to stop the program to read the OB1. So at each cycle, if there is a new OB1, it executes it. So this is the principal weakness that the hacker can use to inject here block or another block. I choose OB1, but we can inject another FB or FC into the PLC. So this is the code source of the function that we use to generate the block and injected it. So this is the function to download, sorry. And this is, so in my code source, I use the hexadecimal of the OB1 and injected it through the PLC. So I want just to show you a video because the equipment doesn't work, that in which we make this attack, and in the same video, so we propose some countermeasure and protection to detect this kind of injection throughout the memory. You can also detect if there is a packet in which the hacker tried to brute force the password or changing the password in using a probe like Suricata or Centrio. Because our objective is to protect the installation, not to hack the installation. So this is the example in which we use. So we have a gun controlled by the actuator, and we develop a small HMI to control the gun. We use a PLC. Here we have a probe in which we say that on the network we have two machines. So we connect. So we connect the ACK machine on the switch. In reality, on the ship we have a lot of points in where you can connect your interface. So then you execute our attack, and here you modify the block that in which we can make moving the gun to the right or to the left. So on the probe, they detect the new machine, so the machine of the hacker, and the illegitimate stream by red color. That means that we have a new stream that we don't know it at the beginning. So in the second phase, so we put the firewall between the PLC and the other architecture, and we try to make the same attack, but here we have the firewall, use the information coming from the probe, and block the attack. Of course, the next step is to hack the firewall to make this attack. At the next step, so we say we put another probe which is called Suricata, and we want to, if the firewall can't block the stream, so we'll try to catch all the event like modifying password through the PLC, injecting a new block or something like that. So the last attack consists of making a random movie of the gun. And here we have the log, the file log of Suricata, which detect the modification of the dynamic injection block throughout the PLC. I put here some picture. This is not cyber attack, but if we don't secure the PLC on this installation, we can have the same problem. We can make a disaster. So we should be careful. And which we propose like some action to protect this PLC. So we propose to configure the password memory protection rather than it's very easy to break it or to jail it, but we should put it. It's Siemens give us the recommendation to put it, so we should do it. We can also activate the now how protect block. So with this protection, we have a flag which, when we download the OB1 from the CPU, we can read clearly the source code of the file. We can also use another configuration in the PLC which called the alarm organization block. So this is a specific block in which we put some action, and when we have, for example, when we try to eject the SD card, we have the OB alarm which catch it, and the information will be sent on the development or on the CAM, another server. We have some example of event that we can catching by the organization block. So uploading code, stop, run PLC, something like that, modifying the IP address. We can also use an industrial firewall to block the suspicion packet. So this action is more difficult because we should to know at the beginning all the malicious packet. But we can put some rules to detect them. We can also use some suricata, as you show on the video, to detect abnormal stream, illegitimate connection, write memory. So this worked very well. And at the end, so we develop a specific script in Python, which frequently download the source, all the source code from the PLC. We compute the integrity checksum by SHA-205.6, and if there is a difference between the check of the integrity code, so we restore dynamically the original program throughout the PLC. So this worked very well. It's a small cyber resilience action. And as conclusion, it is very easy to inject the dynamic cloud through the PLC. You have just to understand how it's works inside the PLC and to download snapshot library. And other PLC manufacturers still have the same problem. So we can make the same demonstration on the, for example, Schneider Modicon 340 or other model. And the new PLC generation should consider this kind or this type of attack. So in return, we have actually a new problem. So we have the sensor and the actuator, like engine, like a probe, like alarm, that are not connected by electrical communication. Actually, they talk Ethernet and Wi-Fi. So in some days, we will be able to connect with the library C directly on the engine and give him some order or some command to stop or to run more and more. So I think that the future of cybersecurity is guaranteed, and especially on the PLC domain. Thank you very much.
Okay, thank you, Nidal. So we have some minutes for some questions.
Hi, thank you for the presentation. I have some question about the probes you talked about. You say that you can detect write memory commands. On most PLCs, you will have some registers that should not be written and some others that should be written. I was curious to know how this is configured, if you have to configure the probes specifically by saying that some registers should not be written.
Exactly.
Or if it's kind of a learning process.
Exactly, that's what we're doing. So in the probe, I can show with some example of suricata, and I can also give you the example of rule if you want after the presentation. And if in the rule we have example, we say the second rack, the 24 offset, I should have this value. If you have this value, that means that is a code injection through the PLC.
And are there some kind of transformation you can? Is it possible to get, for example, a project file and to transform it into rules for the detection? Or do you have to do it manually to re-implement all the constraints into the probes?
It depends, because so use, for example, Wireshark to detect which kind of packet. So, for example, the first 5 packets we have information that means this is a command, and I will inject all the blocks through the PLC. So I can make rule to detect just this first 5 packets, and then I understand that the next packet. Talking about a full injection block throughout the PLC. But I can make some rule on a specific packet, but it's necessary a good memory to detect this on the network.
Okay, thank you.
You're welcome.
Any other question?
I want to say also, if you have a memory stick, I can give you the script of attack. It's not a problem for me.
Hi, thanks for the talk. You spoke about devices that will be able to speak Wi-Fi or wireless connectivity. Why don't you just boycott this kind of devices? They are absolutely insecure by design.
I hope. So the manufacturer have so they dict and they propose this kind of device, and more we can find the previous device. So we don't have the choice, and we should use them.
Well.
We hope that they don't put this kind of equipment, but
So I get there is a
real problem for the future.
yeah, and some financial incentives that you should put forward to prevent this kind of initiatives, I guess. Because, well, France is a big actor, it has money, so I guess.
Exactly.
Thanks.
You're welcome.
Well, thanks again.
Thank you very much.